Welcome to the first of 36 lectures on cosmology. It's a course on the origin and history of our universe. My name is Mark Whittle, and I'm a professor in the Department of Astronomy at the University of Virginia. And I was really delighted when the teaching company gave me an opportunity to put together this course. The reason is that right now, cosmology is an absolutely wonderful subject. It's not hard to see why. First of all, there is no grander subject. Cosmology, let's just define it here, is the study of the universe as a whole, its origin, its growth, its nature, and its future. It is currently one of the most active branches of astronomy, which of course is the larger parent subject and is more concerned with the nature of all the objects that we find in the universe, stars and galaxies and so on, whereas cosmology tries to step back and consider the entire context for all of these objects, the whole. Another reason I was keen is that now is the perfect time to give this course. 10 years ago, the subject, while mature, had several nagging areas of confusion, and I would have had to wrestle with explaining this confusion, which would have itself been confusing. But in the last 5 years or so, the results of a number of major observational programs have very convincingly resolved these problems and brought a level of clarity and coherence never before seen in the subject. In a way, we're the first generation ever to know in some detail and with fair confidence just how the universe came to be the way it is. I'm speculating here, but I wouldn't be surprised if 500 years from now, these 2 decades will be seen as a period of breakthrough, not unlike the periods of discovery we associate with names like Copernicus, or Newton, or Darwin, or Einstein. Now, although in this case there is no single name, nevertheless, one might say that right now is when cosmology has finally come of age. Now, in this first lecture, I have 2 main aims. In the second half, I want to provide a roadmap for the coming lectures, to outline our journey ahead. But in this first half, I'd like to provide a more historical and even sociological framework for our subject. So cosmology, of course, is not a new subject. It has broad and very ancient roots. Essentially, every culture throughout history has a worldview within which there is a cosmological account of creation, how the people came to be and how the world was made, and often how the universe was made. Usually, of course, these accounts take the form of myth. Now, myths are complex and multifaceted things. Often told in poetic form, they usually express deep human truths woven into an explicit account of creation. And so, as such, they have a cosmological component. So I think it's appropriate to start this course with these traditional creation stories. In a way, they're the emotional and social heritage of our subject. Now, there are hundreds of such stories, but I'm going to pick just 2 to get a feel for them. The first creation account comes from the Bantu peoples of Central and South Africa, and it goes like this. Originally, the earth was nothing but water and darkness. Mbombo, the white giant, ruled over this chaos. One day, he felt a terrible pain in his stomach and vomited the sun, the moon, and the stars. The sun shone fiercely, and water steamed up in clouds. Gradually, the dry land appeared. Mbombo vomited again. This time, the trees came out of his stomach, and animals and people, and many other things. The first woman, the leopard, the eagle, the anvil, monkey Fumu, the first man, the firmament, medicine, and lightning. Nchenje, the woman of the waters, lived in the east. She had a son, Woto, and a daughter, Labama. Woto was the first king of the Bakuba. This is a delightfully visceral and human account of creation, and it places us up close to the starting point of nature and its people. I wanted to take the second example from one of the current great world religions, And of course I could have chosen Genesis, but precisely because many of us are familiar with that, instead I've chosen the creation account from the Sikh religion. It's written in their most holy book, the Guru Granth Sahib, and I've abridged it just slightly. For millions upon millions, countless years was spread darkness, when existed neither earth nor heaven, but only the limitless divine ordinance. Then existed neither day or night, nor sun or moon. None other than the sole Lord was visible. As it pleased him, the world he created. Without a supporting power, the expanse he sustained. Brahman, Vishnu, and Shiva he created, and to Maya attachment he gave increase. Creating continents, spheres, and netherworlds, the hidden he made manifest. Creating the universe himself, he has remained unattached. The compassionate Lord, too, has made the holy centre, the human being. Combining air, water, and fire, he created the citadel of the body. Displaying his power, he himself, from the void, created inanimate things. From the unattributed void were created air and water. Raising creation, he dwells as monarch in the citadel of the body. Lord, in the fire and water of the body exists thy light. This is also superbly evocative, placing the creative agent deep inside us. It also clearly addresses an issue that we ourselves will have to address, and that is, how does the universe come from nothing? This is an idea we won't shy away from, and will return to a number of times during the course. Now, before I compare directly these traditional creation accounts with modern cosmology, let me very briefly mention what are usually seen as the historical and intellectual roots of our own modern scientific approach to cosmology. They come from ancient Greece, exemplified here by Plato and his student Aristotle. It's often said that it was here that the notion of a rational, understandable universe was first fully embraced. And so from careful observations of the night sky, they envisioned the following structure for the cosmos. At the centre was a spherical Earth, surrounded by concentric spheres on which the planets were fixed, the outermost containing the stars, and beyond that, the eternal fire. This particular view remained almost unchanged for over 1,000 years, in part because it became interwoven with Christian theology. But in time, starting in the late 16th century, the intellectual climate shifted sufficiently for new ideas to be incorporated, and through characters such as Galileo and Copernicus, Kepler and Newton, the path towards our modern approach to cosmology became defined. So how do we, or even should we, compare traditional creation accounts with modern cosmology? I think there are clearly some differences, but also some similarities worth pointing out. First of all, modern cosmology constructs its account very differently. It's very much a science, drawing upon extensive observations that are interpreted in a theoretical framework that is itself drawn from a mature understanding of physics and mathematics. But despite its firm footing in rational, empirical methodology, the story that is emerging is far from emotionally sterile. As I hope you'll come to realise, in many ways, modern cosmology tells a tale as gripping and powerful and inspiring as one might wish for in a creation story. And for drama and intricacy, it can easily compete with more traditional creation stories. Now, unfortunately, because we're not yet very familiar with the subject, much of this course will be absorbed in the scientific, intellectual realm. But right here, at the beginning of the course, I want to encourage you to try routinely to step back and see the bigger, almost philosophical or even spiritual picture. which is that ultimately this is the story of our deep lineage, our relationship to the universe, and how everything came to be the way it is. Given a choice between struggling to understand the material in scientific terms or gaining a simpler, intuitive and even emotional appreciation, I would always favour the latter. Now let me say a little about the course, its level and its approach. First, the level. Obviously, doing cosmology, for real, requires a deep understanding of astronomy and physics and mathematics. But it transpires, perhaps surprisingly, that almost every topic we encounter can be understood in simple, intuitive terms. So that'll be the primary style of this course. Now, occasionally, I will support some of the discussion with simple math, because for some people, that makes the subject more robust. But if you're not a math person, just let that go by. You won't need to follow it in detail, since I'll always restate what's going on in simple English. Secondly, the approach. There are various options, not all of which work very well. One is to take a historical approach, following the story of human discovery. But since the history of discovery is full of blind alleys and confusion, it is itself a confusing story to tell, especially if you don't already know the plot. Another option is to take things chronologically, starting at the Big Bang and coming forward, or perhaps starting now and going backwards. But this doesn't work either, because at any given moment, there are actually several stories unfolding in parallel, and one really needs to follow them separately. So I've decided to be very goal-oriented and to try to tell you as clearly as I can the most important themes of modern cosmology as they are currently understood. Obviously, I'll include some of the story of human discovery, and the chronology of the universe will, of course, emerge. But my primary aim is to convey to you what today's cosmologists understand for the origin and evolution of the universe and the things they find in it. Now, before I map out the trajectory of this course, let me briefly mention the overarching context within which everything will be framed. It's called the inflationary hot Big Bang theory. It had its beginnings in the 1920s and 30s, when cosmic expansion was first discovered, raising the possibility that the universe wasn't infinitely old, but may have had a birth with an initial explosive origin. There was a rather dormant period until the 1960s, when the microwave background was discovered. This suddenly confirmed the Big Bang as a very credible cosmological theory, and also suggested the early universe was very hot. Hence, it's the hot Big Bang. In the 1980s, a possible launching mechanism for the expansion was introduced. It's called inflation. Hence, it's the inflationary hot Big Bang theory. Then in the 1990s and early 2000s, increasingly impressive observations have stunningly endorsed this inflationary hot Big Bang theory. And hence my statement earlier, that we live at an unusual moment in the history of cosmology. So with that lightning historical perspective, let's use the remaining time to look ahead to the path this course will take. I've divided the remaining 35 lectures into 8 distinct themes. First, I'll take 8 lectures to provide an overview of cosmology. We need to get the big picture before we can dive deeper into the subject. So we have one lecture that introduces the hierarchy of structures. It's a sequence from smaller to larger, from planets to stars to the Milky Way, to galaxies, to clusters of galaxies, to the deep universe littered with billions of galaxies. Another lecture looks at the overall form the universe takes. It has no centre or edge. In fact, every location is essentially equivalent to every other. It embodies a deep principle of egalitarianism. But there is also a dual nature to the universe. It is smooth on the largest scales an endless uniform mist of galaxies stretching out in all directions. But it's also structured and lumpy on smaller scales. So there are galaxies scattered here and there with great gaps in between them. Another lecture looks at the fundamental stuff from which everything is made. There are 5 elements. Things we're familiar with, atomic matter and light, and things we're less familiar with, neutrinos, dark matter, dark energy. At different times in cosmic history, each has their important role to play. In another lecture, I'll review the whole history of the universe, from the Big Bang right through to today and on into the future. We'll take a couple of lectures to explain how distances are measured and how these lead to the discovery of cosmic expansion. And we'll conclude by looking at the universe's 2 most enigmatic components, dark matter and dark energy, which together make up 96% of everything there is. In our second theme, we begin our more in-depth study of cosmology by first stepping back to look at the universe's more global properties, its spatial geometry, and its expansion history. Here we're interested in applying the theory of gravity, Newton's or Einstein's, to the universe as a whole. With the universe expanding and matter inside pulling back, a critical question is whether it will turn around and collapse in a big crunch, the opposite of a Big Bang, or carry on forever. For most of the 20th century, answering this question was a holy grail. I'm pleased to report that many observations in the last decade have finally provided an answer. It will expand forever, and furthermore, and this was quite unexpected, its expansion speed will gradually increase as the billions of years pass by. One of our main aims will be to understand why this accelerating expansion occurs. It turns out that when space itself weighs something, rather than slow the expansion down, its natural tendency is to fall outwards, picking up speed as it does so. For the third theme, we'll visit the first 1,000,000 years, equivalent to just the first day in the life of a human. During the first 1,000,000 years, the universe was in its fireball state. Everywhere was brilliant light and deafening sound. Perhaps surprisingly, when we look very far away, we look back in time and we can actually see this fireball state. It appears to us all around the sky as a very uniform microwave glow. This is the famous cosmic microwave background, and it provides a goldmine of information about the properties of the universe. In fact, this information is extracted using an acoustic analysis. The sound an object makes tells us about its properties. In this case, the object is the universe, and the microwave background allows us to analyze its sound. So in these lectures, we will actually listen to this primordial sound. But perhaps most importantly, the microwave background shows us the beginnings of lumpiness that will ultimately grow into galaxies. This brings us naturally to our fourth theme, which takes 6 lectures to tell the story of how ever richer structures emerge as time passes, how the primordial sound waves grow to form the first stars, which gather to form the first galaxies, which gather to form the first clusters, and how the web of galaxies emerged. You can see this patchy web here, in this map of the positions of about 250,000 galaxies, where we're located at the center, looking out on either side to about 2 billion light-years distance. Understanding how these patterns emerge is currently a very active area of research, and because its complexity is so great, it often requires very powerful computer simulations. Here's one just to give you the feel. It shows how a relatively small region of the universe expands and begins to clump up and form small galaxies, which over time merge to make larger ones. And ultimately, the entire system becomes a huge cluster of galaxies. The calculation includes literally millions of particles and applies Newton's laws of gravity over a time spanning almost the full 14 billion years. The simulation ends with a zoom in to look at the structure of the cluster of galaxies that formed. We'll also track the evolution of the entire population of galaxies, starting with first stars born just 200 million years after the Big Bang, then through the first infant galaxies in the first 2 billion years, which can now be studied in quite some detail by using the Hubble Space Telescope to look extremely far away and hence back in time. It turns out that galaxy youth is wild and chaotic, a time with common galaxy-galaxy collisions, like these lovely nearby examples. But over time, things settle down, and by about 6 or 7 billion years, we begin to finally find the kinds of galaxies we know so well, with nice spiral patterns or smooth elliptical shapes. This part of the story also includes understanding how massive black holes first form and then grow right at the centers of galaxies. And it turns out these black holes can significantly affect their host galaxy and even prevent it from growing larger. It transpires that the entire history of galaxy formation and growth is a finely balanced collaboration between dark matter, which provides the framework for assembling galaxies, and atomic matter, which is able to fall into pockets of dark matter where it can form stars that ultimately become galaxies. It's really a fabulous story that's only recently been well understood. One of the wonderful aspects of cosmology is that it deals not only with huge things like stars and galaxies, but also it's concerned with tiny things like atoms and atomic nuclei. So our fifth theme will visit the micro world of atomic nuclei to find out how all the chemical elements were made and explain, for example, why gold is rare and iron is common. In a sense, we're looking at our own matter's deep ancestry. As you may know, tracing the lineage of our own matter takes us to the centers of stars, which one can view as atom factories. In fact, the energy released when new atoms are made is what makes the sun and stars shine. Stated more poetically, the starry sky is a direct indication that new atoms are being forged. Perhaps those new atoms will one day find their way into the brains of sentient beings, just like the atoms that now give you sentience were once made deep in the hearts of stars that lived and died long ago when our galaxy was young. In Theme 6, we'll take 3 lectures to visit the very early universe. Very early here means the first second. Now, this may seem a bit ridiculous to spend 3 lectures on 1 second, but a second seems only short to us because it's essentially how fast we can think. But nature's clock runs immensely faster than our thoughts. And so to nature, this 1 second is an immense tract of time in which many things can and did happen. One of the defining features of these early times is that the universe was exceedingly hot, much hotter than the center of the sun. And so we need to understand how matter behaves at such extreme temperatures. Well, it may surprise you that physicists have built enormously complex machines that can reproduce these conditions. They're called particle accelerators, and they've been able to generate the conditions 1/100th of a nanosecond after the Big Bang, when the temperature was 100 million times hotter than the center of the sun. There are about a dozen wonderful phenomena that are worth looking at during that first second in the universe's life. How the 4 great forces of nature took on their current form, and how the many particles emerged and changed as the temperature dropped. We'll also learn how the early universe contained almost equal amounts of matter and antimatter. And for reasons that are still not fully understood, following a brief period of almost total annihilation, a small amount of matter was left over, from which you and I and everything around us was made. The story to this point in the course is called the standard hot Big Bang theory. And while it's very impressive, it can't explain several deep puzzles. What is needed to explain these puzzles is a launching mechanism for the expansion. And that brings us to theme 7 of 4 lectures that look at inflation. During inflation, which occurred very early, within the first nanosecond, the conditions in the universe made it fall outwards very rapidly, so that when those conditions turned off, the resulting expansion was on exactly the right track to make the big, old, empty universe that we find around us today. We'll also learn that during inflation, tiny ripples in space caused by quantum fluctuations were amplified, and it's these that provide the seeds for the growth of structure: stars, galaxies, and the galaxy web. This is an extraordinary notion, that subatomic quantum fluctuations are ultimately responsible for the construction of galaxies and their billion light-year patterns across the sky. But that's not all. One of inflation's more remarkable properties is that it's able to create the whole universe from essentially nothing. It manages to make equal and opposite amounts of positive matter and negative gravitational energy, the two summing to 0. And if that were not impressive enough, inflation may also be able to make many universes, not just ours, raising the possibility that we actually might live in a multiverse, not just a universe. Now, while the details of inflation are still unknown, the evidence for it continues to increase, and there are some exciting possibilities of testing for it in the near future. In our final theme, we'll take 3 lectures to return home and take stock of where we are, pausing to see where we fit into all of this. We'll look at the so-called fine-tuning problem, namely, if the constants of nature were only slightly different, the universe would be quite sterile, not allowing complexity, including ourselves, to arise. This introduces the so-called anthropic arguments, in which our very presence places strict limits on what the constants of nature can be. Now, whether there is anything spooky in the fine-tuning is still hotly debated. We'll also look at what's next for cosmology. In the coming decade or two, obviously, cosmology is extremely active, and there are many wonderful projects planned or soon to be completed. And finally, we return to a question that Einstein once posed. The most incomprehensible thing about the universe is that it is comprehensible. Why is it that we can discuss what happens billions of light years away, or in the first second after the Big Bang, when we've evolved here on an extremely unusual and cozy corner of creation? I'll suggest that much of the character of the universe is in fact all around us, even here on Earth. And having evolved within nature, we are indeed her children and can speak her language. In the end, it may be that our modern cosmology will provide that sense of lineage and belonging that is such a strong part of our more traditional creation myths. Thank you for joining me on this course, and I hope you find the journey and the places we'll visit as wonderful and inspiring as I do.